Hello and welcome to part 4 of Dev Maths and Stats Refresher Course, Lecture 9. Now we turn to the important subject of sampling. We have a few demonstrations of this. The first demonstration is in this spreadsheet, normal samples, and it's taking many samples of size 50 from a normal distribution. So here we've got the setup. These are the population characteristics. So I've set up the random variables to have this mean, zoom in so we can see, this mean, this variance and this standard deviation. And then based on this, the same as in the previous video, I'm generating a sample, a relatively small sample as well, of 50, smaller than 1,000. So each of these numbers here is based on this mean and this standard deviation being generated by the same normal formula as before. As before, every time you press F9 or do anything, it generates a new sample. Okay, now to move to the more realistic scenario, when you're actually doing any applied work in the real world, normally you do not know these numbers here. This is normally unknown. When you go and visit an area, you don't know what the average income is, what the standard income is, how much time women spend collecting water, how many migrants per year on average goes to the city. All this stuff is unknown. You're going there to try and find it out. But what you do have in these situations is the sample. So what you want to know is, can you, from this sample, can you get some estimators which let you estimate this? So this is unknown. All you can see is the sample. Based on the sample, can you try and estimate these things? And if so, how accurate will that be? So that's what we're going to try and do. So we can't do anything based on this because it's not known. So if we're just given a sample, so we just have these 50 numbers, how would we, for example, work out what we think the mean is? Well, obviously to try and work out this unknown mean, all we can really do is look at the mean of this sample. And you can see that the mean of the sample is sort of not far from the mean, but it's not exactly right. If we take another sample, it's too much. Another sample, it's a bit nearer, too little. So it's not bad, but it's not exact, but it's impossible to get perfection because it's impossible to know exactly what this is. But that's a way of estimating the mean. This mean we should really call the sample mean to distinguish it from this one, which is the population mean. And what you'll see is, in terms of notation, this unknown mean is normally known as this, mu. This is the population mean. The sample mean is usually referred to as this. Yeah. So this is, if you've got your x1, x2, x3 your sample, this is the mean of these. And similarly, this standard deviation or the variance, that's known as that. That's known as this. So these apply to the population. We need to get some estimators that will estimate these. So the first is the sample mean. Okay, what about variance and standard deviation? We only talk about estimating the variance because the standard deviation is the square root of that. So we just want to find an estimate of this, and then we can get the square root with that. So let's look at what we can do there. Well, again, if we want to get the standard deviation of the population, all we can really do is work out the standard deviation of the sample. However, you notice I put two ways of doing that in here. And the way that these differ is that when you're working out the standard deviation, you should know that the process is you find out how far is each of these numbers here, you subtract the mean, and then you square the difference, and then you add all of those squared differences up, and divide by 50, because there's 50 in the sample. That will give you this number here. If instead you divide by 59, you get this number here. So in this case, you're dividing by n minus 1, where n is the sample size. Here, you're dividing by the sample size, n. So you get two slightly different answers. That's why this one comes out slightly bigger, because it's divided by 49 instead of by 50. Okay, well, as you can see, the variances, they sort of come out, these are both too high compared to that. These are both too low. These are too high, much too high, too low, and so on. So again, they're never exact, but they're kind of in the right ballpark. But the next part of this demonstration is to show you that even though normally when you go and do a survey, you take one sample, we can't really understand how close your sample is likely to be to these true population numbers unless we think about, okay, what happens if we take many, many samples? Then we can see it's like pressing F9 many times. You can get an idea how good is this. So what we're going to do is, quite simply, select all of this stuff, like so, and copy it along here, so we get lots and lots of samples. And that's what I've done on the next sheet. It's just that it's already done for you. I've added in some rows, which is why there were rows above left blank. So all of these samples are based off the same population, but we don't know these values. We have to imagine we don't know these. We're trying to estimate what they are. So in every single case, I've worked out, I've got these three estimators. That's the sample mean based on those numbers. And then we have two estimates of the variance. That one, where we're in the calculation divide by 50, and this one where we're dividing by n minus 1, which is divided by 49. Okay. And then what I've done is looking at all of these, I'm trying to compare how close they are to that. So this, just for the mean, that's the mean of all the sample means. And we're getting very meta here, so that the mean of the means. So that's the mean of all the sample means, you can see, is pretty close. Yeah. And that's just a variance showing how much they vary either side. So variance is about 3.2. So I should put the standard deviation there. The standard deviation, oh no, okay. SQRC, that's the standard deviation of that, 1.9. So if you double that, it's about 4. So 99% are, or more than 90% are within 4 of that, so it's quite close. Here we're just counting how many are underestimates, how many overestimates. That's a nice way to see whether it's biased or not. So are you more likely to get an under or an overestimate? So you can see that if I just repeat it a few times, you're getting more or less the same number above as below. Sometimes more below, sometimes more above. But always it's pretty close to that 34.8. So that means a pretty good estimator. Now look at the variance, and the variance, we're trying to estimate this. You can see here that they're both underestimates. So this one's slightly closer. They're both underestimates. Variance, you can square it again to see how close they are. So around about 100. Square, no, not 100. 30 or so. But this is the one that's more interesting, is the under-overestimate. You can see in this case, 150 overestimates, only 103 underestimates. This has got a slightly better balance. A few more examples of this. So again, many more underestimates, many more overestimates. Again, yeah, always more overestimates with that one, and closer with the other one. So, and this is like the textbook case. You can show mathematically that this number 2 turns out to be a closer one. You're more likely to get a balance of under and overestimates. And this one you can mathematically show is biased in the sense that you're more likely to get an overestimate than an underestimate. when you use this version, when you divide by 50 or n, compared to when you divide by n minus 1, or 49 in this case. So in practice, what we use is we use the mean, the sample mean as the estimator for the population mean, and this form of the standard deviation, which is called the sample standard deviation, where you divide by n minus 1, is a better estimate than the standard deviation of the actual numbers, where you divide by n. And so that's the one we use on that. This is written with a small s. So this is x with a bar above it. This is written with a small s. Notice the difference with the formula in. And here, this one is written as var p. So I'm working out it's called the population variance. So this is dividing by 50, assuming that all I want to do is describe the spread of these numbers. So these are all the numbers I'm interested in. I use that. But much more common is that these numbers are taken as a sample from a larger population. What I'm trying to do there is to estimate the variance of the whole population. So this one is the sample variance, and that's the default. So you just put var and it works out the sample variance. If you have a calculator with variance and standard deviation on it, it will default to this version. It will assume you want the one which divides by n minus 1, unless you force it to do the other one. So let's see what we conclude from that, hopefully, back here. So conclusions are, when you're taking estimates from this normal distribution, the sample mean follows a normal distribution, and the mean of the normal distribution is this. And then this is claiming that the standard deviation of that distribution is the original standard deviation divided by the square root of n. You can see that on here, that this is the mean of the means, the variance of the means. If you take the original variance divided by 50, then you have the variance of the sample means. So these sample means here, they also follow a normal distribution, and the variance of these sample means is the original variance divided by the sample size, 50. And as you can see, it predicts it quite closely. That turns out to be really useful, as we'll see in a while. So the distribution of those sample means is normal, follows this distribution, normal distribution. It's a good estimate of the population mean. So x bar is a good estimate of mu. This is the population one. This is the sample mean. But when you turn to the variance, the sample variance is a better estimate of sigma than the population variance. So in the next video, we look at some further properties of these sampling distributions and estimators. But for now, thanks for watching.